Okay, you might be wondering how a transmission line can be infinite in length. In the real world, it must be of finite length. However, it's for the sake of simplicity, we start with an infinite transmission line. This approach is useful because with an infinite line, its structure is uniform everywhere, which simplifies the analysis. We can arbitrarily cut a small piece out of it to analyze its properties. In this circuit model, the voltage difference between the nodes at position x and x plus delta x is equal to the voltage drop generated by the current flowing from the left through the resistance R times delta x and the inductance L times delta x. This is precisely what the first equation on the slide describes, which uses a partial derivative with respect to time t. This is because at position x, the voltage of the inductor and the flowing current are only related to time. Let's examine the second equation. When the input current I of x, t flows to the output junction, it will split into two currents. One current flows to the output I of x plus delta x, t, while the other current flows to the following conductance G times delta x and capacitance C times delta x. This current is equal to I of x, t minus I of x plus delta x, t, and is the sum of the currents flowing through the two components G times delta x and C times delta x. One of these currents is V of x plus delta x, t multiplied by G delta x, while the other is C delta x multiplied by the partial derivative of V of x plus delta x, t with respect to time t. Our goal now is to use these two equations to determine the relationship between the voltage and current waves at position x. Since we are talking about a small line segment, its length is delta x. Both equations have delta x in them, so we can move delta x to the left side of the equation and rearrange the terms. If delta x is small enough, then V of x plus delta x, t will be approximately equal to V of x, t. The variables on the right side of the equation are related to position and time, but what we cared about is their rate of change with respect to time. Additionally, we can write the differential expressions on the left side of the equation as partial derivatives of the voltage and current waves, where we cared about the rate of change with respect to position. The last two equations we obtain are famous telegraphers' equations, as known as the transmission line equations. The waves on the line are not only time-dependent, but also position-dependent. The next challenge is to solve the voltage and current waves from these two partial differential equations. It might seem difficult to solve, but it's actually quite simple. So let's continue.